Hey guys, what's up? Eddie Alho here with KissAnalog.com. Alright, hey, today I've got this Class D amplifier. I've got a playlist of videos I've been doing on this. They've been spread out over a few months, I think. And I just want to get this in a box and get it done, okay? So what I want to do is I want to find out how much power I can get out and how much I can count on. Now, Michael Beanie, if you guys have seen his videos, I'll put a link down below for his channel. He's done a bunch of videos on, well, he's done a number of videos at least on this amplifier board, and he's found problems with heat sinking. The thing just can't put out a lot of power for a while. The voltage problems, put too many volts on this. I haven't run into those. I've got two different boards here, the one here and this one here, and they look different. They have different parts on different capacitors, different op amps, and different regulators. They just have different parts. Some of them are the same, and I'm going to kind of go through the parts on another video, just kind of put everything together. But for now, I just want to do some temperature testing to see how much power I can get out before they do actually thermally shut off. The nice thing is they do thermally shut off safely, and they come back up and they work again. So they are designed well in that they don't blow up. Now, he had a problem with his little regulator here that provides 12 or 15 volts, and he had a problem with one of those heating up. Now mine, both of them, I've put 51 volts on. I can adjust my switching power supply from right around 45, 46 volts up to about 51 volts. And I've applied 51 volts on both of them. Been fine. So, but as far as putting wattage, putting a nice voltage signal out, I find that if I go up to say 24 volts, 25 volts, it shuts off pretty quickly. The device gets so hot that it gets hot so quick that it doesn't have time to let the heatsink pull heat off, and that's partially due to the coupling of the device and the heatsink. We can improve on that. For now, I'm not going to even try. I just want to see what I can get the way it is right now, okay? But I will. What I'm going to do is I'm going to do it on the bench with no fan, and then I have these two fans, a bigger one and a smaller one, and I'm going to show you what those fans do for us, okay? So it's kind of an experiment. I'm kind of learning here as I go. So let's go ahead, come over here to the bench and take a look and see what it does, okay? What I'm going to do is I'm going to try a couple different voltage levels. I'm going to crank up the output, and I'm going to put both channels on 4 ohms. So we're going to kind of do, maybe not worst case, not like 2 ohms, but we're going to put 4 ohms on each one, and we're going to see how much power we can get out without any fans and see how long it takes to shut down. And depending on that, we might go directly to fans, or we might just keep on creeping up the power until it does start shutting down. Now, one thing I do want to mention, these are sine wave tests where we put sine waves in. Amplifiers are meant to play music, not sine waves. So if, and we'll do a video on this too. When you look at, I'll play music through this, and you can see the dynamics, the amplitudes, and just the basically empty space where nothing's happening in between notes and that. Whereas sine wave, especially 1 kilohertz, what we're doing now, I mean, it's kind of brutal actually. So it's really what some people call a bench test. It's not, doesn't have anything to do with how much power it's gonna put out with music. Now, here's the bad thing. What some people do is they kind of taper down the power output because they don't want to thermally shut off or things like that. So the reason I say that's a bad thing is because for music we want dynamic range. We want to be able to put out those peak power levels, and we're not going to do a sine wave continuously. It's just not realistic. but I do want those dynamics so that when some note jumps up there, you know, it can. Okay, so I don't want to limit that. I want to let my dynamics go. But so this test is just kind of like, hey, well, let's see what it can do. You know, it's a sine wave test, and then after that, we'll say, okay, that was cute, but now we're going to put music through it. So then we'll determine, you know, how much power we're going to get or how much dynamic range we're going to have after that. Okay, does that make sense? What do you guys think of that? Give me your comments down below. Okay, so here we go. We're gonna go ahead, come over to the bench, try a few different voltage outputs, and you know, if we can get up 25 volts and let it run there for a period of time, even at a sine wave, then I think what will happen is for music, when it wants to jump up there and put out that wattage, then it can. You know, it's not going to do it continuously, so I'm not going to be concerned with that. It's not, and if it does overheat, it shuts down, so no problem there either. But I do want to see how much cooling I need to do, because it'll give me, I can extrapolate a little bit, you know what I'm saying? So if I can put out, say, 150 watts dynamic and 50 watts continuous, then that'd be cool. So, get it? Cool. Alright, let's just do it. Let's come over here and try it out. Nice. So this is the bench right now with the switching power supply that I'm going to power this thing up with, okay? And the amplifier, I am running the input signal right here into the back end, and the inputs are both shorted together. So the generator here, that signal right here, is coming from this new junk tech that I reviewed not too long ago. Okay, so what I'm doing is I'm going to use this little Fluke IR probe, just to kind of probe around for temperatures. I could use my thermal camera too to take a picture, I guess, but I just want to spot check a few things. And then I'm using meters up here, which have a little glare on them, but I'm using this one for the AC voltage coming in here, because I'm using a variac over here just to dial things up. And I'm using this Hioki to read the DC voltage to see what I have, because I can dial the voltage and adjust it to about 6 volts difference, I think, from we'll look, I think around 51 to 46 or something like that, 45. Okay, and then I'm using the Mixig scope so I can watch the signal, and I'm using that Keithley over there for the distortion measurements. Okay, and then scrolling up here, I've got that Kaiweets power supply, 12 volts, running the fan down here on the bench. Okay, so looking back at the bench, I've got this fan, but I'm not running it right now. First I want to do is I want to run this at a decent level of power, just see how long it'll run before it thermally kicks off, because this heatsink will eventually heat up and click off. And I've done some testing, so I'm getting kind of a feel for things, but let's go ahead and do that. Now remember, we're just running sine wave, 1 kilohertz. So music power, it's dynamic. It's not going to be like this. It's not average power at all. It's kind of a fault in the way we test with sine waves. But anyway, I've got these 4 ohm resistors hooked up. So first I'm doing a 4 ohm test, and then I'll do the 8 ohm test, okay? So, and then I'm using this Hioki meter here. If you can see the display, I don't know if you can see it. But I'm using a Hioki to measure the temperatures with this. So this guy's just going in here, and I've got it on the volt scale, and when I turn this on, it takes a moment for this guy to adjust itself, and then it comes up 22C in the lab right now. Alright, so let's go ahead and power it up, and I think I'm going to take this to 16 volts RMS on the screen up here. So we're going to get, I think, 16 volts RMS, and we're going to see how long this thing will run with no fan. Just, you know, until this thing heats up and turns off. I just want to get a feel for how that works before we include a fan. Now this guy's kind of a big one. I don't know if that's the one I'm going to put in the box. And that's part of the experiment, because I also have a smaller one like this that I can place maybe right on top of it, or maybe, you know, somehow fix it to the top. I'm not sure. We'll see. Okay, so let's give it a try. When I power up this switching power supply, there's some lights you might see through here, and there's also some lights right underneath here that'll come up. And so let's see what happens. I don't know if you can see the lights over here, kind of blue ones, and there's some red ones right down in here. See that? Okay, and right now there's just one LED. Okay, I had to power cycle it, and both LEDs actually came up that time. I think my input signal was still on when I powered it up, and it went right into clipping protection. So, and when it does that, it basically shuts itself off and doesn't start back up again. All right, so I think we're focused on there. So yeah, when it faults, it comes up and it kind of just crowbars. Now, let me see, I probably need to turn some lights off so you can see the screen better. There we go. Okay. All right, guys, so I'm going to go ahead and bring it up, and I'm going to bring that up to, I think, 16 volts. Okay, 16.3. Maybe I'll dial it in just so we know exactly how many volts we have. Okay, that's right at 16 volts. All right, pretty darn close. All right, so let you look at the screen there. And I got 1.868 volts peak to peak going in. All right, guys, there we go. We got 16 volts, and we're running, and I'm timing it, and I'm gonna go come back after it thermal shuts off. Okay. All right, just show you what the input is like right now with 16 volts on the screen, 16 volts RMS, and that's with 4 ohms on each output. So we have both our left and right channel, 4 ohms with 16 volts RMS. All right, guys, so that's 64 watts at the input, right? Or I mean on the output of each load. So we got 128 watts total. And here, let me turn on this fluke probe here. Okay, 23.6 just pointing into there. And when I point at the capacitors, they're not very hot. The coils, the two middle ones, they heat each other, so they get the hottest, of course. The capacitors in between, they're not hot. And this is 344 into the test. I got some black electrician's tape over here so I can get a good reading. See, we're up to 93.6. So it's getting hot. Now, I can go look at this little regulator over here. Not bad at all. The inductor for the regulator, not bad at all. Little caps. I can just look at all these things right here just for fun while we're letting this thing heat up. The little caps next to the heatsink get hotter. These caps, I'll measure the temperature real close to the heatsink. They're not soaking in too much heat. 97. If I go electrician's tape, about the same. So this little IR meter works pretty good. Okay, we just shut down, guys. It's about 4 minutes and 40 seconds into it, shut down. And, you know, things are already cooling down pretty fast. So let's go over here and look at the resistors. See what 64 watts does to a 200 watt resistor. And we're up to about 49 degrees on this. So it's starting to get warm too. This one looks a little bit hotter, 52. Maybe I'm not on a hot spot right here. Get a couple of degrees hotter on the electrician's tape, not too much. 52. Yeah, maybe just depends where I touch it, but yeah. Then here on the ends of them, 49. So yeah, that was 64 watts going into a 200 watt load for just over 4 minutes. Alright guys, I'm using this fan to cool things down fast. It is this fan right here, 12 volts, 0.4 amps. If I put my air kill anemometer on it and get that thing really spinning up, you can see the speed. That's feet per second. So it's a pretty good fan. Okay, I don't know if I'm going to put that in the box. It's not too noisy. I mean, if you're playing music that loud, I don't think you're going to hear this fan maybe. But, and maybe I'll need that to get the power. But I was going to try maybe something like this right over the top of the heatsink too. Alright guys, I just powered this thing back up again. I let it cool about 8 minutes or something with that fan blowing on it. Okay, the fan's still blowing on it. So now, let's see if I can bring this up to 25 volts. And it's going to shut down pretty quickly, I think. Well, with the fan blowing, actually I think it'll run at 25 volts. I think this thing will run for a while. Okay, there's 25 volts right there. And I have 2.97 going in. Yeah, you know, I did this once before, and I actually didn't wait for it to thermally shut down. It ran for a few minutes, I believe. So I think it'll run. I'll come back when it shuts down, okay? Alright guys, that was only about 2 minutes, and I was kind of playing around so I didn't stop my watch, but it was about 2 minutes and it shut down. So that was with the air blowing on it. Here, let me show you that. Set just like that. So about 2 minutes with 25 volts. Alright guys, so 25 volts in, that's squared, and then 4 divided. It's 156 watts, just over 156 watts into each channel. So that's putting out over 300 watts. And it did that for about 2 minutes. Okay, with the fan going, I'm going to power it back up. And it's cool. It's not totally cooled down, but I think it'll be okay. So what I want to do is I want to take it to 16 where we had it before and just show the difference with and without a fan. Okay, there's 16, a little bit over. Okay, that's about 16 volts. And let's just see if it will run there for a while. All right, we have about 0.56 total harmonic distortion, 0.56. It sounds bad, but really it's mostly from the generator. It's almost all from the generator. So, yeah. So I didn't see it really increase at all with the amplifier. We still have the signal. It's only been about 3 minutes, but I've been taking some temperature measurements. I want to show you that, and it's kind of stabilized. So let me just show you what I've done. Just show you what kind of temperatures I'm seeing. Again, this is with the fan going, so of course we're going to get cooling from that. Here, let me bring it over here. So this is, okay, this is my blue mat, 22.4. And here's the caps right by the heatsink. They're staying pretty chill. Inductors even. It's pretty amazing. Little airflow. Well, you know, decent amount of airflow maybe from that fan, but everything's staying super cool. Look at that. Super. Now here's the heatsink on that black electrician's tape. It's barely climbing. You can see how slow it's climbing, if at all. I feel like it's almost stabilized. So up here on top on the, I don't know how well this thing works with the emissivity on the shiny surface of the heatsink. So I go down here where the air is blowing on it, so maybe it's cooler there, I don't know. But even if I go underneath it, try to, I can't really see anything getting hot. So I think with the fan, this thing's putting out 300 watts into 4 ohms. Well, 150 watts into each 4 ohm load. So that's a total of 300 watts. The switching power supply is cool. I think it's capable of over 600 watts, so it's totally cool. So there we go. Now the resistors are definitely heating up. Okay, now look at this. Okay, I'll check out the map first. Okay, then look at this resistor. It's nice and toasty. It's getting a little bit of airflow on it maybe. So these resistors are pretty toasty. Even the resistors with that air, they're even climbing pretty slow. All right, guys, so I got my thermal camera out here, right? And it's gonna put red on the hottest thing, even if it's cool. And I'm seeing 23 point, almost 24 degrees on some things, but I had this running and I just cooled it down. But wow, it's kind of funny how that cap is the hottest thing right now. Look at my finger, it's much hotter. And my fingerprint stayed on the capacitor. So yeah, it's kind of funny how, instead of just making everything cold like this bar graph right here, it's going to automatically rescale the graph, and the hottest thing it's going to find is going to put red. And if I put that marker, it's like 24 degrees. So if I put the marker over there on my mat, it's like 21. So about 21 in my lab, and that thing's a few degrees hotter just from, that's interesting why that one's hotter. I'm not sure why, but here, let's go ahead and turn on the power supply. You hear the fans kick on from the switcher over there. It's not too loud though, right? What do you guys think? Now look at that heatsink starting to warm up. And this one cursor that jumps around looking for the hot spot, it's starting to find it. And if I move my center cursor right on it, I can track that temperature. Well, I'm seeing about 34 degrees. Up here I'm only seeing 28, so it's not quite tracking it. Huh, that's interesting. All right, so the regulator up there doesn't look bad at all. It's this heat sink. And I've only got about 8 volts right now. So I'm about 8 watts, I guess. No, it's 4 ohms. Sorry, 4 ohms. So each channel has a 4 ohm resistor, and each channel is putting out 8 volts. So 64 divided by 4. So about what, 16 watts right now? Okay, I'm going to go ahead and increase it. I'm going to bring it up to like 16 volts where we had it in that previous test, where I kind of tried to see how long it would stay there. Okay, that I'm just bringing it down. I went over a little bit. So, all right, right there. Now I can see this red one. It's about 47 degrees right now. The coils, if I come over here and focus on them, they'll turn red, but they're only 26 degrees. So that's one nice thing about this camera, is you can just kind of get it close so that it rescales for the area that's inside the camera. See over here where the leads are coming out? They're actually a little bit warm, right? 4 ohm load, so we got a little bit of power. If you want to see the loads, they're right there. And they're like 37 degrees right now, so they're starting to get warm. Okay. And there we are. That's what the board looks like right now in the thermal camera. So it is kind of nice to have a thermal camera, because you kind of look around and see what's going on. You see how the heat's spreading, how well it's spreading through the board, that kind of thing. We're up around 75 degrees. It's getting hot. It's going to turn off, and it turns off in about 3 minutes, I believe. Now, if I turn on this fan right here, it'll cool that right down. You want to see that? Okay, the fan's going. We're around almost 80 degrees on that heat sink. It's starting to cool, 78 degrees. 77. So yeah, that fan does wonders. And over here, those coils about 29 degrees. One over there on the edge about 25, 26. Yeah, they're probably around 28 degrees if I hold it there long enough. But with the fan, we're starting to see the heat sink cool down at 74. It probably would have switched off by now, but see it's 72, so it's actually going down in temperature. So that tells me I'm going to bring up the power. We're at 16 volts. I'm going to bring it up to 20, and that's 21. Let's bring up 25 volts. Whoop! I went up 27 and it shut right off. Temperature on the heat sink's like 72, but that chip heats up a lot faster than it can send heat into the heat sink. So there's a little thermal time lag there. So yeah. Anyway, this is a sine wave. It's not music, so it's, you know, it's kind of hard to correlate the two things because sine waves, I mean, got to be a lot more power than music, right? All right, guys, I replaced this big fan with this little one and just used a little tape to keep it right on top of that heat sink. And look at that. It's kind of funny. The center of the fan's getting kind of warm. I mean, you know, it's because it's the only thing that's running. Still not hot at all. So, okay, let's go ahead and turn on the power supply. And I'm going to turn it to 16 volts. Okay, we're almost there. 16. Okay, we're at 16 volts. So we will see if that little fan can keep this thing running. All right, started my watch a little bit late, but let's go ahead and try it. Okay, guys, I started my watch, you know, about 20 seconds late. So it's about as much time as it ran before when it switched off. And right now, this thermal camera looks like 49 degrees, maybe the hottest thing. But look at the inductors. Now they look like they're almost as hot. You know, I mean, the heat sink's definitely still hotter, but the color difference, these things are about 30 degrees in the middle. Yeah, maybe even 35, the hottest spot. And up here, it's about 50 degrees, the hottest spot. So there we go. That's the picture of the fan. You can see the fan spinning around there, right? Pretty cool. Now, if I push this button, if you haven't seen me show this camera before, it goes all photograph and then all thermal. Then we can kind of step in between. So pretty cool now, huh? That little heat sink did a good job. Now with the power supply running, the power supply over there is actually louder than this little fan. So now here, let me lock this guy in. Okay, so that was the fan speed. That's the speed of that thing. What is that? 10.39 feet per second. 62 degrees in here. 36 relative humidity. So this is pretty cool. Now I can put it in front of this fan and kind of compare it to this fan, just kind of give you guys an idea of the airflow. I'll do that in a minute, okay? But yeah, we're about five and a half minutes into it. And that heat sink's staying under 50 degrees. Okay, now what I'm going to do is I'm going to creep up the voltage. Okay. Okay, I'm at 16. Oh, shoot, I jumped right up to 24. All right, I'll leave it there. Let's see how long it stays there. It's going to get hot fast. Hopefully the fan will be able to keep it cool and the chip doesn't get too hot. The fan's right in the center of the heat sink, and that's where the chip is underneath, so that might help. But it's really the thermal interface between the device and the heat sink, which we can totally improve on that, but I wanted to do kind of before and after. So I'm at 58 degrees. I see the little hot spot over here. If I point my arrow at the side of the heat sink, It's about 57, you can see here. But look at the inductors. Now everything's kind of getting hot. The inductors are 35 degrees. I'm seeing 38 degrees on this red thing, the hot spot. But when I point the center cursor, I'm seeing 36 on that one. About a little bit more, pretty close to the same. And over there, maybe about the same. I'm kind of amazed that we're still running, guys, because we're 7 minutes into it. And kind of lost track of how long we've been at the 25 volts. But yeah, we're at 25 volts hanging in there. Okay, it just clicked off. And that's about 7.5 minutes into the test. So you got to add some time to my watch there because I didn't start it for about 20 seconds or so. All right, here, let me peel this off there. Wow, look at that little guy. He spins pretty fast, doesn't he? 14.2 meters per second. Or 4.2 feet per second, I mean, sorry. Pretty cool, huh? So that's the fan. 12 volts, says high speed. Wind Sine, dual ball bearing, but I don't see a current level. Here, I'll stick it back down there and do some more testing with that fan blowing on it. All right, guys, I want to show you something. I'm running this at 20 volts with that little fan. I'm just kind of curious to see if we can get it to run a ways with that. All right, guys, one thing I want to show you is where I've placed that fan. It's that's a different board. Obviously, these Nichicon caps look a little bit bigger, right? But anyway, it's sitting right here, so it's kind of level. It's almost level. These caps are a little bit taller, and this heatsink might be a little bit shorter. I'm not sure. It's definitely thicker, but part of the blades are pushing air down into that hole there, which I'm hoping, you know, hits the board and goes underneath to the part that's, you kind of see the compound or the thermal pad right down there maybe. Yeah, you might be able to see the little thermal pad right there. So just trying to get a little air down in that way and then then cool the heat sink. Okay. Okay, I want to do one more test. This time I'm going to use this nice little temperature meter I got from Eric Hill. Okay. Go ahead, let's turn on the power supply. All right, I'm starting my watch. Try to get it started this time on time. And then let's bring up that signal. What I want to do is bring it up to 20 volts this time. Right at 20. A little bit over right now. Okay, that's just barely over. All right, so with this, you can see the little, whoops, you see the LED right there? So I can shine that and see what temperatures I'm getting. See, if I shine on that shiny surface, I'm wondering if that's going to give me a good reading. I can shine the coils. So I kind of aim at what I want to hit. See, let me move it so you can see what I'm doing. There's the capacitors, nice and cool. And the regulator over there looks nice and cool. The inductor as well. Now, I'm going to come over here, and when I let go, it holds it. I'm going to come over here and hit the tape on that heat sink. There we go. That's a little hotter. Okay, now let's hit the heat sink here again. It's not quite as hot. I think it's those shiny surfaces. So if I come over here on the tape, I'm getting about 40 degrees still. So interesting, when I go off the tape near the bottom of the heat sink, close to the chip, it does actually give me a hotter temperature. So even though I'm on a shiny surface, it still actually shows a hotter temperature. The tape is almost at the bottom, so you might be able to see the LED shining underneath the fan. I got temperatures close to 40, like 39, 40, but then it's kind of bouncing around underneath there. Now I'm getting about 46 degrees over there, so things are heating up pretty slowly. Getting the inductors here in the middle. Get this inductor over here on the side. Here, I'll hit down here on the bottom of it. So that's what I'm seeing there. Get that inductor here. Let's try to hit all the way around it. If I get these middle ones, and the capacitors are definitely cool, so it's a good thing that temperature's not getting into the caps too much. Yeah, about 27 degrees. And that fan right there in the center is about the hot spot of the fan where the bearings are. If I get nice close, there's 34 degrees. And I'm not getting, yeah, so if I get up closer, I'm getting a better temperature, or a hotter temperature reading. That's about the hottest temperature reading I got over there on the side. And look at that, I got a little bit hotter on the top of the fins. So yeah, I just kind of move it around. So yeah, you can definitely do it with this. And then the thermal camera, let's bring that back into action. And I'm seeing 55C, the hot spot. If I point the center screen on that heat sink, I'm getting about 50. And the inductors, I'm getting about 35, maybe 34, 35, 38 maybe there, I don't know. So, wow, we're at 5 minutes at 20 volts with that little fan. Guys, so we're at 5.5 minutes, and look, there's my heat sinks over there. I can smell them getting hot. Over 100 degrees C. 100, yeah. Look at that. They're pretty hot. And I'm seeing 51. You can see that. 50, 49, 50. Yeah, I'm pretty impressed. That little fan is doing a remarkable job for just being a little, it's a fairly quiet fan. The fan on that power supply is louder for sure. And there we are. So I'm seeing 55 degrees, the hot spot. It's not bad at all, guys. We'll save a picture. But look at those heat sinks. I'm seeing 128 degrees at the hot spot. So, you know what? We're at 7 minutes. I'm going to go 10 minutes and then I'll probably shut down. All right, guys, we're still going strong. It's almost 9 minutes. My junk tech over there. The scope up there showing my signal. And our temperature readings down here. So, here, let me show you the thermal camera. Because we're coming up on 10 minutes. I think I'm going to just shut down 10 because my resistors are getting super hot. They are, look at that. 130 degrees, 138 degrees a hot spot. That's pretty hot. And show you with this guy. Yeah, 121, 127, 130. Look at that, 130C. Those things are hot. Meanwhile, the inductor's about 30, under 40 degrees. They're 37 degrees. The outside ones are a little bit cooler, maybe. I don't know. This one seems pretty hot. The heat sink, about, it hasn't changed. It's been about 50. If you get, whoops, there you go. Sorry. Try to make so you can see it. I'm trying to feel around 45 degrees, 46. And if I come over here on the side where I get the hottest temperature, I'm looking for it. It's been stable. It's been about the same temperature, which I'm trying to find right. Oh, I just missed it. It's just over 51 degrees, 50.8. So yeah, that little fan has done wonders. Okay, we're almost 11 minutes into it now. and I think I'm going to shut down. Oh, and by the way, the THD is 0.56, which is mostly coming from the generator. So yeah, just want to throw that in there. It didn't change throughout the test. All right, so we tried a few things, right? And my thermal camera, tried that. Oh, and I also have this experiment going on with this battery. I'm going to do a video on this. I got this Hioki. It's a really cool meter. And I've got this battery that I'm trying to restore. I'm trying to see if I can. You guys got any tips? I'll be happy to hear. This is one of those kind of gel type for my Jeep. So, yeah, it's expensive. I let it drain too low during COVID and stuff like that. And just didn't drive it. And, yeah, it had to put a new battery in. But I want to see if I can, you know, put life in that. So let me know. So we use this little IR gun, this new thing. Yeah, pretty cool. Eric Hill. I think this is a pretty nice one. And I believe that, well, I'm not going to say what the price is. I'll have to look it up, okay? But we tried that. Then I got this Eric Hill thing where I can check airspeed. So we kind of played around with the different fans. It's kind of neat. That little one actually puts out a lot of speed, right? Speed. There's speed and volume. You can actually put the volume in that so it'll tell you how much cubic feet you're moving. But I just kind of been showing airspeed. And then I got my old, you know, tried and true fluke that I've had forever. So with the Hioki, which is, these Hiokis are, I think they might be my favorite meters. So anyway, all right guys, so what did we find? We found that we could put out 100 watts continuous. I think 100 watts continuous, no problem with that little fan. So that was pretty neat. 100 watts into each channel into 4 ohms. So, you know, going backwards linearly, that would mean 50 watts into 8 ohms. I feel that if you have 50 watts into 8 ohms, you should have 100 watts into 4 ohms. Your speaker, so yeah, you know, if you have an 8 ohm speaker system, 4 ohm speaker system, yeah, what does that really mean? Because, you know, the 8 ohm speaker, depending on the kind of speaker, it's going to have different impedances at different frequencies, right? So as it does that, you don't want your amplifier changing power levels non-linearly. You want a linear power level. You want a constant voltage. Well, you know, you want this, whatever note you're putting out, you want it to be able to do that. And just because it's a different frequency and your speaker changes from 8 ohms to 4 ohms, well, if that happens, the power has to double or else you're going to have distortion. So yeah, anyway, so that's the way I think about that. 2 ohms, it needs to double again. You know, if you're going to have 2 ohm you know, impedances in your speaker output at different frequencies. Anyway, okay, kind of going down rabbit hole, but this thing here, that little fan seems like it does a lot of good. I'm going to put this in the box. We're going to see what that does for us, heat sinking and stuff like that. And I think I'm going to take that little heat sink off and put a pad the full length of that heat sink so the heat from that chip will immediately spread across the full length of that heat sink into the board, into the heat sink. Okay, so that I'm going to try to do that, and I think I think that's going to do some good for us. Okay, so I'll try that. I'll do it before and after, another video for that, and that'll be maybe a short video showing just how to do that. And then the next video will be showing putting this in, you know, assembling it into my box, and then off to my friend's house so he can listen and compare it to the Class A amplifier that I designed. I have a playlist for that if you haven't seen it. So, sorry about the long video, but I think we covered it all. 2 thumbs up to my patrons. Appreciate you guys. Been awesome. You know, it helps me buy some of this stuff. So, it really helps offset that kind of expense I have. And I need to start selling some equipment, by the way. But, alright. Hey, and you know, I've had a couple of people just recently hit that that thank you button down below where you can do a one-time donation and buy me a cup of coffee or something. Really appreciate you guys doing that, and that's been awesome. And God, that's just I just think that's really cool. You guys support the channel. You can support the channel also for free by liking the video, subscribing, and using the links down below to buy this stuff. Or I got a bunch of links down there, so it doesn't cost you anything extra. Free way to support the channel. So yeah, it's pretty late. It's been a really long week, a lot of late nights, and yeah, I got to get up a few hours to go to work, and it's still going to take me another hour or so to upload this video. So all right, thanks guys. Sorry I haven't got more videos out. I've been gone a lot. I had to do some traveling and stuff, and this is my first weekend where I'm going to be home and I'm going to get some videos out. So yay. You can tell my energy is kind of low today. I'm pretty beat. It's been a long week. Did I mention that? Thanks for watching, guys. We'll see you next time.